slide is visible and I am audible properly?
Yes, yes, you are. Yes, yes.
So I am Mahua from CSE Department, MCKV Institute of Engineering. And I'm going to present my research work, that is retinal image patch retrieval. Retinal image patch retrieval using Siamese quantum neural network. So thank you organizers for giving me the opportunity to present my research work. This particular work has been published in the year 2022 in IIT Quantum Communication. And these are the outlines of my presentation. Actually, we have executed our experiment in 2 different phases. First of all, retinal fundus image retrieval using Siamese quantum neural network, and then the fundus retinal image retrieval using NEQR circuit, that is novel enhanced quantum representation circuit. Retinal fundus images are actually 2D retinal images which are captured by a special purpose camera, and different retinal ailment symptoms are prevalent on retinal images. For example, microaneurysm, exudates, hemorrhages, etc. Among all those different ailment symptoms, we have dealt with exudate, that is the lipid deposition on the retina. What we can say about retinal damage is that the main point is retinal damage is irreversible in nature and which ultimately leads to blindness. That is why early detection and treatment is very necessary for retinal damages. And retinal fundus image retrieval actually helps in automated computer-aided diagnosis of different ocular and circulatory diseases. As we can see from the block diagram that database images and query images are actually processed and they are compared, and similarity score is measured, and according to the sorted similarity score, the similar images are retrieved. We are dealing with content-based image retinal image retrieval, and we are retrieving retinal image through Siamese network architecture. Siamese means twins. From the diagram, we can see that if the images are passed through 2 identical networks, then the intermediate feature representations here in this diagram, the intermediate feature representation fx1 and fx2, say for example, they are compared with the absolute difference between them. And in this way, the similarity measurement is computed. If it is greater than a particular threshold value, then it can be said that the input images are not similar. This is the underlying principle of Siamese network architecture. And we have used, and what is the important point regarding Siamese network architecture is that the less the difference between the samples, the more similar the images are. And Siamese architecture avoids network training requirements as part of its implementation principle, as we have seen in our previous slide. We have implemented parameterized quantum circuit or quantum neural network within the Siamese network architecture to retrieve affected retinal images. Here we can see from the diagram that the ground state, that is gate 0, is passed through some unitaries, then some quantum gates are applied upon them, and at the output end we are getting the measurement values. And when the parameterized quantum circuit or the quantum neural network, this is actually trained, the training optimization is taking place in the classical computer. And in this way, we can say that the training of quantum neural network is can be considered as quantum classical hybrid method. The implementation framework that we have used, the first experimentation we have used, one of our experiment we have executed in IBM Quantum Lab using QIQT, and another experiment we have executed in Google Spark environment, though it has no significance that why we have executed in two different environments, but we have executed in two different environments. The evaluation metrics that we have used to evaluate our retrieval system are mean average precision and mean reciprocal rank. The precision is the percentage of relevant retrievals among top k retrievals. K is the rank value. And for mean reciprocal rank, we have considered the rank value of the first similar retrieval. The data set we have used for our experiment is E-optha dataset. E-optha dataset actually contains two different subdatabases. One is microaneurysm hemorrhage subdatabase and another one is exudate subdatabase. We have used exudate subdatabase for our work implementation, where we have got a total number of 82 images. Among all those 82 images, 47 images are having the symptoms of ailments, that is symptoms of exudates, and 35 images are healthy images. Different resolutions are available with those images in the dataset. Ground truths are also available in the dataset. We have extracted from we have considered for our work only the affected images, and we have extracted 20x20 resolution overlapping patches from all these affected images. And on the basis of threshold values, we have decided whether a particular extracted patch is healthy or unhealthy. In this way, healthy and unhealthy images are decided. Now, from all those 47 affected images, we have extracted a total of this many number of affected patches and this many number of healthy patches from all those 47 exudate affected images available in the data set. And for our experimental purpose, we have used 2475 affected patches and 2500 healthy patches. And our patch database, query patch database, consists of 250 exudate affected image patches. This is the outline of the dataset preparation phase that we have already discussed, where overlapping patches are extracted and the patch database is formed. Now, the experiment, first phase of experiment, where we have retrieved retinal fundus images using Siamese quantum neural network. To face with the challenge of decoherence, we have converted the 20x20 image patches to 4x4 resolution, and a lattice of 16 qubits has been formed. And 2 qubit gates are applied in the quantum circuit, and at the output end, we are getting the measurement of the circuit. These are the three parts of the PQC we have used. This is the block diagram of that QNN model that I have already told. And this is the implementation details. We have used the Spark environment and implementation details of Siamese quantum neural network retrieval. These are also the block diagram for implementation details. Now, this is the model summary of parameterized quantum circuit. And now, regarding the similarity score computation and retrieval of quantum neural network circuit. That is, we have considered absolute difference between two intermediate test patch tensors, that is query patch tensor and one database patch tensor, to compute the absolute difference between them. And according to the sorted distance, the patches are sorted, and according to that sorted order, the similar images are retrieved. This is the quantum circuit we have implemented. Now, regarding the result that we have obtained while we have implemented quantum neural network within Siamese architecture. A particular sample query patch we have considered, this particular patch we have considered, and in the left side table we have shown the K value we have considered over here equal to 10. So 10 maximum similar image patches that are retrieved that we can see in the left hand side table, and for the ease of visualization at the right hand side, those 10 patches which are retrieved, those are shown in the right hand side image. That is, this particular one is the query patch and the 10 similar patches which are retrieved for our visualization purpose. Similarly, another slide I have, in another slide also I have taken another patch, and similarly the 10 similar image patches, and those 10 similar image patches are visualized in the right hand side figure. Now, we have considered some of the image patches, and for k equal to 3, that is rank value equal to 3, 5, and 10, we have considered, and maximum average precision we have obtained is this. Similarly, for reciprocal rank, we are always getting the first similar image in the rank value 1. That is why the mean reciprocal rank we have obtained is 100. That is rank equal to 3, 5, and 10 we have considered, and the mean average precision for the system we have obtained 98.1336%, and rank value of the first retrieved similar sample is always 1. That is why the mean reciprocal rank of the system we got 100%. Now, regarding the second phase of the our experiment, that is retinal fundus image retrieval using NEQR circuit. The NEQR novel enhanced quantum representation algorithm, according to the algorithm, the pixel value encoding of 2 to the power n scale image requires n qubits. So for grayscale image, it requires 8 qubits. For grayscale image, it requires 8 qubits. And if the image is of size 2 cross 2, then to represent each pixel position uniquely, we require 2 qubits. So to represent a grayscale image and of size 2 cross 2, we require a total of 8 plus 2, that is equal to 10 qubits, according to NEQR algorithm. Now, this is the way how to encode the pixels using NEQR algorithm. We are taking one example, and with the example, we can understand how NEQR algorithm is actually implemented. Here, 4 pixels we have considered, and the 2 cross 2 image, so 4 distinct pixel positions. The pixel positions are indicated by 2 qubits in the IDX0 and IDX1, and the grayscale image is indicated by intensity 0 to intensity 7, these many qubits. Now, with the pixel positions, that is IDX0, IDX1, the 1 bit is encoded with a Toffoli gate, that is a CCX gate. So if we consider the least significant from the least significant bit 001, 00110, in the same way, 1 qubit is represented by the Toffoli gate, this one, and this one. So in this way, the pixel positions are encoded. This is the formal representation of NEQR algorithm. Now, if I take one arbitrary grayscale image, for example, then these are the 4 pixel values, say 51, 100, 3, and 96. If these pixel values are, then this particular image, 2 cross 2 image, grayscale image, can be encoded following NEQR algorithm in this way. We have implemented NEQR implementation in IBM using IBM QIQT. This is the description how NEQR circuit of a 2 cross 2 quad of a 4 cross 4 image patch has been encoded, that we have already discussed, which we have not mentioned in the diagram. That is only one C1, that is classical wear is there. C1 represents the classical wear. This is the probability for observables. And now regarding the similarity score computation, we have considered Jeffrey's distance that indicates how similar two discrete probability distributions are. So this is the formal equation where P and Q indicates two discrete probability distributions. In our case, we have used Jeffrey's distance to compute the divergence between two different probability distributions, one of the query patch, another of the database patch. And in this way, we have computed the Jeffrey's distance, and according to the Jeffrey's distance, the images are sorted and similar images are retrieved. So regarding the NEQR circuit implementation, we have considered K equal to 3, 5, and 10. The experimental mean average precision in this experiment, actually we received 52% and mean reciprocal rank is 71.36%. The result could be maybe more impressive, but in this case, it is not that much impressive. So similarly, if we consider different sample patches for this experiment, so for K equal to 3, 5, and 7, this is the precision values and mean average precision value is this much. And for this particular samples, the mean reciprocal rank is this much. So now the discussion that is specific to the experiment that we have executed, the points are actually we fed two image patches simultaneously to two identical circuits of the Siamese network. And pairwise distance measurement between the feature representations we have computed. And as the implementation principle of Siamese network, we did not require any quantum neural network training. And images we did not resize directly to minimize the medically insignificant information loss. And patch sizes were experimentally selected as 20 cross 20 as further reduced patch size are not supposed to cover the exudate symptoms properly. That has been selected experimentally, decided experimentally. Now, the general discussion regarding our work is that the special characteristics of superposition makes the quantum execution faster than its classical counterpart. Our quantum machine learning has the power to capture the entanglement among the states. And we suppose that entangled states can represent the solution space effectively. So this is the comparison with other fundus image retrieval works that is available in the literature. Most of the works that is available in the literature are machine learning based or deep learning based. So as conclusion of our work, we can say that we evaluated the parameterized quantum circuits within Siamese network in the Google Circ environment, and we received the mean average precision of 98.13% and mean reciprocal rank of 100%. We also experiment with another retrieval approach, but the result would be more impressive. And what may be the, in conclusion, I can mention then why I have executed this experiment actually. Because classical machine learning algorithms already proved itself very efficient in identifying patterns. But the classical neural network models suffer from some time and computation exhaustive training using huge data. And to overcome some of these limitations and to find out some of the alternatives, I have implemented this one. And further, some limitations are there in our work. Particularly, we have executed in the simulator, all the experiments we have executed in the simulator. And we have implemented the circuit, but we have not incorporated any error correcting codes. So the error correction part we have not addressed. So that may be the limitation of our work that we need to address. And similarly, some other limitations and future scopes of our work we are mentioning over here what are the ways we can improve our work, because this is the initial phase of our implementation. And these are some of the references that I have used during my presentation. So with this, thank you everybody. And if you have any question, please ask me the question.
Okay, thank you very much for this talk. So the floor is open for the question.
Hello, ma'am.
Yes.
Yeah, please.
Is this implementation is connected with our brain function, because we are discussing neural network and retinal diagnosis?
Means neural network is actually mimicking our brain function. Classical neural network, I'm telling about the classical neural network. But in this case, we have implemented quantum neural network, means the parameterized quantum circuit. So in this implementation, as the parameterized quantum circuit parameters can be adjusted and optimized to get more and more better result to represent more effectively in each of the iterations. That is why parameterized quantum circuit is considered as the quantum version of the neural network. So in this way, we can say that it has some connection with the classical neural network. Otherwise, I think it is not connected with our brain function. So many classical works have been executed on retinal image identification, analysis, etc. But quantum neural network application yet not verified in this particular field, medical imaging field. So that it is not that much verified. But we had just started our work to verify its efficacy in this particular field. I think it will be effective.
One more question. How we are implementing the quantum circuit and what we are discussing in retinal diagnosis?
Actually, I have explained in my slides how we have implemented this one. We have implemented in 2 different phases, as I have told. I'm now telling you how we have implemented it in Google Search environment, that is inside the Siamese network architecture. The same quantum neural network. This is the implementation details in the SARC environment. The same quantum neural network, 2 patches, that is one is the database patch, another one is the query patch. These patches are parallelly sent to the same quantum circuit, and the intermediate tensor is extracted, and the similarity between, that is absolute difference between that 2 tensors are computed, and according to the absolute difference, the patches are sorted, and those sorted patches are retrieved according to the K value. This is the way.
Thank you, ma'am.
Thank you.
Okay, is there any other question? We have a few minutes.
Can I ask a question?
Yeah, please. Please.
Thank you for your talk. Could you please explain why are you not using machine learning as compared to neural network? Because machine learning, they can also recognize image patterns and can be useful as compared to neural network. So could you please explain?
Yes, actually in the field of retinal image pattern identification and analysis, we have the classical neural network or different image processing techniques. Those are already proved themselves as very efficient. But we are trying to find out whether the quantum neural network application are quite efficient in that similar field also, because with the application of quantum neural network, we can execute the similar algorithms much faster, as well as number 1 point. And number 2 point is with the quantum entanglement, whether we can capture the feature correlation more efficiently. That is actually our motivation to verify that. That is actually our motivation to implement this one.
So you mean that quantum neural network, they contain quantum entanglement, and those can be used to speed up the recognition process.
Speed up the recognition process as compared with their classical counterparts. Similarly, I can assume that I'm assuming that it can capture the feature correlation between the pixels very efficiently, entanglement. So that is the two motivations. That is why I am trying to verify my thinkings.
Okay. Okay. But in quantum imaging, if you look at the quantum imaging, and that process is heavily utilizing quantum correlations to reconstruct the image. So I'm just thinking why you are not using quantum imaging concept in your search.
Actually, what I'm trying to say that with the second phase of implementation that I have already mentioned, that with any QR implementation, that is any QR algorithm is how to convert an existing digital image to quantum image. So from that point of view that you just told me, from that point of view, I tried to verify any QR algorithm, so that I can convert that 4 pixel or 16 pixel image to the quantum counterpart, quantum image, using any QR algorithm. But we have computed Jeffrey's distance, that is the probability difference between the probability distribution. But in that case, we have not received that much efficient result. But what is the reason behind it, that I have not found out till now. But in that second approach, actually, we converted the actual digital image to the quantum counterpart, its quantum counterpart.
Thank you. Thank you.
Okay, so let us thank Dr. Paul once again. So thank you very much. So please unshare your slide.